All right, everyone, how are we doing today? Doing good? Tired? Me too, man. I felt that. So we're recording. Hopefully our laptop is charging. So let's see. Brought my old document camera just in case. So how's the lectures going?
They're fast.
They're fast? What'd you guys talk about?
Linear systems, time shifting systems, and I think he ended off with bounded and unbounded systems.
Yep. Bounded and unbounded systems.
It's just like classification.
Let's see. Let me just click on my files. You like that? Comp assignments. Let me just pull this out just in case. Boom. And pull that down there. I think I was given a question. Let me see. Let's go through my emails. Does this look like your guys' exam?
Yeah, I talked to Joanna during her office hours, and I kind of just emailed her, just hey, can we kind of maybe go over some of the questions, and she told me she had reached out to you just to see if maybe you could go over it as well.
Yeah, sure. Let's see. Well, here's a problem. It's flipped. Let's see. How do I rotate?
Top left.
Oh, there you go. Thank you. There we go. Let's see. Consider our analog signal. I love our analog signal. Let's see. Okay. Let me just, here's my visualizer thingy. Boom, full screen that. They need to give me an extra 30 minutes, like a lecture, so we can go over all these problems. I wonder if there's a switch. Give me a second, y'all. I don't like the shadow. Is that a lot better? Yes,
I
sir.
would prefer it dimmer, but it does just a little bit.
Yeah, look at that line in the middle. What do you think?
I don't know what to really think.
Let's keep it. Someone complains about what's the giant black rod in the middle. It's just a shadow. Someone said, what's the snake doing here? I don't know, man. Talk to the shadow. Anyways. So, let's do EE360D. Let's call this week 4. Is that what it is? September 17, 2025. Put 1 right there so I can remember what to print. Focus. Yay. Anyway, so I'm going to teach everyone something about signals and systems. All signals and systems, or signals. You guys know how to define a signal? You guys remember those equations or those definitions in your book?
Yes.
It's going to come back. I'll tell you that. Exam 2. So anyways, I'm going to practically tell you what's going on. So if you've already taken our labs, 221, 320, or currently taking them right now, let's just consider some signal. I'm just going to call it A, or let's not use A. Let's just use something that's everyone's familiar with, X, right? It's going to be a function of time. And do I want to do that? Yeah, let's just do that for now. Signal X of X, or X of T. It's a signal that's based on time, right? I'll tell everyone now, every signal is going to have an amplitude, e to the j omega t. And it's going to have some kind of phase. Is that correct? Magnitude. Right? And then phase. All good? But there's another coefficient I'm going to try and introduce to everyone. So you know how you have this is a phase, right? There's also going to be another term here. I'm just going to call it, I don't know, just some amplitude. And this right here is also a real part. How do I say this? It goes with your signal. It's like an attenuation. attenuator alpha, right? You want me to explain what's going on? So I'm just going to dissect this signal. So we already know that every signal is going to have an amplitude, right? I'm going to do the following. E to the alpha t. What does that mean? So it's just, this is an exponential, right? Let's just say our alpha term is 0, right? What does that mean for this? Just 1, right? So actually, let me just do the following. E to the j omega t. Is that good? If, let me see. I need to put this, guys. Page 2.
Are they added or multiplied together?
They're added. Or not added. So we have, let me just go over this one more time. This is going to be our attenuation, right? That's going to be a value that's going to be a real value. It's going to go up, it's going to go down, it's going to be DC or whatever it's going to be, right? Is that understood? This right here is just a phase. And most important, it's just a spinning term. All it does is just spin around in a circle. It's a sine, it's a cosine, it wiggles up, it wiggles down. I'll draw you guys some pictures, and I might have to skip a lot of steps to show you why you're doing this. So if I were to talk about just e to the at, right? And I'm going to have 3 cases. Alpha is greater than 0. You want me to do that? I'm trying to do this. Alpha is equal to 0, right? And then alpha is or less than 0, right? So let's just say, for example, e.g. alpha is equal to, I don't know, 1 or something like that. Or infinity. Infinity, if you want to call it that. And then this is just 0, right? And then I'm going to say alpha is like equal to -1 or minus infinity. I'm just putting this as an example, right? So in time, right? I have a signal in time, right? And it's got an alpha term, right? If our alpha term right here, this attenuation term, right, is a positive number, what happens to this exponential? Right? If this is a positive value, right? And t is going to go forward, right? Right? So that means this whole term is going to be positive, right? Right? And as time goes to infinity, right? What happens to this term? It's going to go to infinity, right? So when alpha is a positive term, there's a positive term times your time, right? You're going forward in time, right? Let's just say e is equal to 0. I'm just going to draw this. Is anyone bothered if I do e to the 0 as this point right here, call it 1, or actually, better yet, alpha, right? So let's just say alpha is equal to 1, right? So now we're just looking at e to the t, right? What happens to e to the t as time goes to infinity? Right? Does that make sense? Now let's just say our alpha term is equal to, I don't know, I'm going to use a different color so I can explain to you guys. No, I don't like that one. Let's use pink. -1 volt, right? So now I have a signal minus e to the positive t, right? It's just alpha to t. I'm looking at when alpha is equal to, it's a positive number, right? So I'm at, let's just say e to the 0 is just -1, right? Right? And as time goes to infinity, it's just going to go to infinity, right? Does that make sense? What I'm trying to say right here? Good? Anyways, so now let's talk about when alpha is equal to 0. So now we're looking at a e to the 0. That's it. All right? What is this equal to? Correct, right? So if time goes to infinity, right? Does it bother anyone if I do this? It's just a DC voltage, right? So that means if I were to do like, I don't know, A is equal to -2 volts, -2. Does that make sense? Is that good? Now let's talk about when A is less than 0, right? Can anyone predict what's going to happen? Is that good? Easy? And then, well, if I want to do that, I think I know what someone's talking about. This is actually triggering some things I don't like. Because if we have a minus alpha term, -1, but it goes to no. Sorry, guys. This term goes to infinity, right? But infinity times this minus, right, gives us negative. So that's actually wrong. Sorry. This should go like this. It's going to some infinity value. It's exploding. Does that make sense? All right, thank you. When I did this, I'm like, that's just a DC shifted signal. I don't like that. Did anyone catch what I was trying to do? Yeah, I just did a signal plus DC, and that didn't make any sense in my head. I was like, what the heck? So like if I had an amplitude where it's like, oh, it's less than like this, it's going to do like this, right? Does that make sense? When I was trying to, if I change alpha to be a positive or a negative number, eventually it goes down to some value 0 as time goes to infinity, right? Is that clear? Now, I'm going to show everyone what this other term is. This is page 2. And don't worry, this is all going to make sense in the end. We started talking about bounded signals, unbounded signals. So now we're going to talk about, well, let's just do this. E to the j omega t. All right? Now we're talking about things that spin around. So let's just do this. If omega is just a positive number, omega is equal to 0, and omega is a minus or less than 0. So if this is a positive number, right, what happens to our alpha term? So I'm going to do this. Watch this. So if I did a magnitude of this, right, and I have a let me just do this. So, how do I?
I'm sorry, that's the signal.
Let me see. I'm trying to show you guys what I'm trying to do. Let's just say, because you know how e to the j omega t can equal to, let's just say it can equal 0 degrees, right? But it can also, let's just say e to the j omega, let's just do 180 degrees t, right? I'm trying to do something funny like this, right? So what I'm trying to show everybody is this is just a phase. That's all it is. So if I had a sinusoid like this, right? A e to the j omega t, right? It's just going around in a circle like that. That's all it is. It's just a phasor. So it's going up, down, it's turning to 0 volts, minus voltage, plus voltage. It's just an AC signal, right? Then what happens when omega is equal to 0? It's just DC. It's just a straight line. Does that make sense? So now, if I were to do the following, T, and I'm going to use a different marker because I don't like this. It's just color that, and color this, make it look like it's normal. So let's just say omega is just a negative number. What does that mean? So we're just going backwards in phase. So you know how cosine goes like this, right? But in reality, if you think about it the other way, let me see. Because if at a is equal to 0, a e to the 0 t or j 0 t, and it goes down to a e to the minus j 90 t, right? We're just moving in phase. So if you think about it, let me see. We start here, but we want to lag this. This one's going forward. I'm wondering if I did this wrong. What I'm trying to say to everyone is just a negative phasor. How do I want to say this? Oh, okay, I'm going to skip a lot of steps. Minus 90 t. It's just going to be off phase by, because it's not going to be negative. It's going to be a 0 here again, too. That's what I'm trying to show you. Let me show you.
But wouldn't it be where you got the 0? Wouldn't your initial point shift over to the 0? So you have your, like, so where the point is at 0?
Yep.
Wouldn't that just go up to go straight up. And the third one, yep. Okay, now go to the 0 point, the one on the t-axis. Wouldn't that point just go up if it's shifted 90?
Shift to 90.
So then that's where you would start right there, right? You're lagging.
Yeah, because what I'm trying to do is a e to the minus j omega t right here, right? And it's just a negative phasor. So as time goes to infinity, this is just going to spin negatively. And this right here, what I'm trying to get to everyone, plus j omega t. I'm going to skip a big step, and it's gonna open your guys' eyes. But this is just a positive phasor. As this one goes forward, if this was 0 degrees, right, and we're trying to go to plus 90 degrees, I'm trying to get to this. You see what I'm trying to say? But I'm gonna skip a really big step if you don't mind me doing that. Watch this. Have you guys taken 431, 432 math?
Yes.
Right, and you guys remember talking about the Fourier transform Fourier series? No, you guys didn't talk about that.
We talked about it, we don't remember.
You guys don't remember? All right, I'm gonna tell you this.
Isn't Fourier the one where you can make any wave out of sine and cosines?
Kinda. I don't want to talk about it because we're gonna skip so many steps. We're technically giving. You know how you did calculus with trigonometry or pre-trig or something like that, and then you learned calculus is just way better. Same thing with Fourier. We're trying not to go the easy way, so I'm going to show you guys a trick. If this was a function of frequency, right, or AKA frequency, right, which is equal to 2 pi f, right, and then I have my positive frequency, right, and this right here is my negative frequency, right. Let's just say I have 1 kilohertz. I'm just calling it 1 kilohertz, positive 1 kilohertz, right, and it's at 1 volt. Right? And I have a line right here. What is that going to look like on our scope? Actually let's not talk about that. Plus omega t. I'm trying to call this something. I'm going to skip lots of steps right here. 1 volt e to the plus j omega t, where this omega is equal to 1 kilohertz, right? Right? Does that make sense? There's a thing where there's conjugates. And you remember how sine is equal to, let me see, sine omega t is equal to, let me see if I remember, Mike, e to the positive j omega t, right? Minus j, yeah, I think it's, is it j? I don't think it is. No. E to the minus j omega t, all divided by 2j, right? Does that make sense? So I have two signals. I'm trying to show everyone this. Plus j omega t minus e to minus j omega t, right? And this 2j, this is just a phase. Okay, this is just 90 degrees. If you think about it, actually minus 90 degrees. So I'll tell you the secret. A sine wave is actually not just a single, it's a real wave, but it's consistent of two complex imaginary waves. This is an imaginary number. This is also another complex number, but adding the two gives you this real value. So for this sine to exist, you need this other counterpart, which is minus 1 kilohertz. Does that make sense? And actually, it's not even 1 volt. It's actually 1 over 2 volts. So when you add these together, you get the full sine wave. Does that make sense, what I'm trying to say? Yeah, so you get two complex signals from a sine wave. So what I'm trying to say to everyone is when we're coming up with these signals for just show everyone what I'm trying to do. A e to the alpha t plus a e to the j omega t, right? Do I want to do that? Yeah, let's do that. This right here is a magnitude. This is your real value, okay? So this is what truly happens in the real world. It'll either go like, I don't know, It's going to go like up like this, or down like this, right? Or it just remains at DC, right? Does that make sense? Right? And this term right here is just a phase. But technically, this term needs another term, which is that like minus j omega complement, because all it is just a sinusoid. That's truly what it is. It can either be this or it could be another signal. I'll just draw this right here. Does that make sense? This is just a phase. All right. So every signal in this course and for the rest of your lives will consist of a magnitude and a phase. The magnitude is what goes up, what goes down, what keeps your system bounded or unbounded. But the phase just spins around. It's going to come back in a circle. Does that make sense? Yes, no, maybe? Because there's another thing, and there's Laplace, but I don't want to touch that right now because Laplace is where this starts making a lot more sense. So let's go over that one problem, the bounded input, bound, and output signal. Let me see. Let's go over that. X of t, don't worry, I'm writing this. E to the alpha t, e to the j omega t, unit step of t. So determine the values of a for which x of t is not a signal, or neither energy or power, a power signal and an energy signal. So I think based on what I remember, and I'll tell you what I got, what I think. So there's an equation for energy, which is also a function of time. And I think that would be the integral from, because what we're trying to do is, I'm going to give you a random signal. I'm going to call this one going infinity. It's going to infinity, right? So if I were to add, so this is my signal x of t, right? And I'm going to calculate the energy of this whole signal. What I'm going to do is, okay, I'm going to go to every point. I'm going to sample every point, right? I'm going to add this all up with some summation. Summation, right? And I'm going to see if I have energy in this. But there's a problem. If I have this kind of signal, it's just going to go to infinity, right? So it's just going to blow up. It's not an energy signal. And there's definitely no power because it's just not there. But if I had a signal like this, like let's just say it's just a blip, that's it. And I go to minus infinity time and to plus infinity time, right? And if I try to do a summation of this signal, like if I try to sum this all up with an integral from minus infinity to infinity, time is equal to infinity of just this signal, right? And I added all that energy, I will get a finite number. It's going to be finite. Finite. Did I spell that right? So it's going to be a number, all right? But is there any power in this? There's energy, but it's not like useful energy where it's like power, it can power our house. Is that correct? So like, let's just say, I'm going to give you another signal. You tell me if I'm wrong. Okay, let's just assume, I want to do, let's just say it goes from, I'm going to do this, I'm going to do this, and I'll complete another period, right? I have this kind of signal, and let's just say it's periodic, right? Now I'm going to tell you this remember from calculus. If you try to sum all the points in this sine wave, right? If I were to add all these points right here, right? These are positive values. It's going to be positive val, right? For just that section, right? But if I have this section right here, which is all neg value, what happens when I add this plus that? It's just zero. There's no energy. It's just going up and down. And this is where all the students are like, but it's a sine wave. It's generating something. You're not wrong, but it's power. There's going to be, if you, let me explain. So I want to capture this signal. I know it's useful. It's going to be useful in a circuit because you use 120 volts on the walls, correct? So I'm coming up with the proof. You guys are going to help me out. So talk about the sine wave, okay? You know if you add this plus this, it's going to be a negative value, right? So that means you have to somehow make sure you do an absolute value, or is it a square term? I don't remember.
It's the absolute value of square.
Okay, because it want to make, so the absolute value is so that, I'll draw it for you, is so that it forces this term, right? This term right here, it forces it to be this, right? So now you can add this. It's going to be a finite value, right? But now you need to square all this. And then you're definitely going to get some values from that, right? Does that make sense? And let's just say, okay, if I'm going from 0 to t, right? And I know if I go from t to, let's just say, I'm just going to draw another one, right? To 2t, right? We know that this right here is the same as this right here. Same. Right? So instead of integrating from minus infinity to positive infinity time, let's just do one period. So now we're coming up with the property 0 to t, right? We're just summing that. And we're just doing x of t squared. Does that make sense? And you know when you add this, it's a finite number. Is that clear? So it's going to be less than, it's going to be, how do I want to say this? Less than infinity, but it's definitely, it's going to be a value. It's going to be finite. Fine. Man, I cannot spell finite. Is that clear, right? All right? But now someone's going to ask me, well, Dave, my signal looks like this. Let me see. Page 6, 7. And I had a student bring this up in class, and I'm like, you're not wrong. Let's just say your signal looks like this. And it's just, I'm gonna do this. Unit step u of t minus, I don't know, 1. And then this is u of t minus, I don't know, t1, t2, right? I'm just going to do 2 weird units. I'm going to do the following. It's going to be cool. 1, 2, 3. There, you like that signal? So I'm trying to create a sine wave that's just on for 2 periods. Right? So add this whole signal. Go from minus infinity to positive infinity. And this is the dilemma. This is what I'm trying to figure out too. Because I even talked about this too. Technically, if I just turn on the light switch and turn it off after 1 second, is that energy? We're using energy, right? So if I were to add from minus infinity time to positive infinity time, isn't technically all power kind of energy in a certain aspect? Yeah, it sounds crazy. So if I were to just do this interval, and I assume periodic, right? It's going to have power. 0. Is that correct? But if it's aperiodic, let me just do this. I'm going to use my, let's use this bluish marker. If aperiodic, if it's just that blip right there, it's just a blip of time, yeah, you're not wrong. There is like no power because, well, That's it. There is some energy if you go from minus infinity to positive infinity of just this signal. There is some power. E to E, which is less than infinity. Does that make sense? Is this making sense what I'm trying to show you guys? Yes, no, maybe? All right, let's reel back, everyone. Let's look at what we have it. Neither an energy nor a power signal. I'll show you. Let's just brute force this. 8. Nine. So let's see. Let's just do it. Click on this guy right there. A e to the alpha t a j omega t, right? So now let's just say alpha is greater than 0, right? So what happens to this term? It's just a circle. It's just spinning around. What happens to this term? And then what's this? Just alpha, right? Is that case? And if I go from, actually, and there's a unit step, right? I think I know what he's trying to do. Because technically, it's going to go from, I don't like this. Alpha t e to the j omega t, because this right here just spin. Is this the definition of energy? Is this what I'm getting? Minus infinity to positive infinity of x of t. Is that the definition?
The integral or limit as t goes to infinity, the integration is from t to negative t, or it's the absolute square value of x of t squared.
Absolute value of x of t squared. Energy? That sounds like power.
No,
Really? Let me see. What is he teaching?
the page in the back is that's energy, and then power is the next one.
X of t squared? Because if you square that...
They're very similar.
They are very similar. And then there's power on the back. Let me see. I like this book. This is thick. You guys like this?
No.
No? You wish it was easier?
I wish it were digital.
Me too. That's what I've been telling you. Okay. He assumes it's periodic. He did not assume it's periodic here. Okay, I think I know what's going on. Absolute value of that too, because you know it's absolute. Okay, I think I know what's going on. Thank you. I appreciate that. So I think the same thing, I think what I was talking about does matter. So absolute value, and I think I know why he did this. Because let's just say I had another signal like this, right? Let's just say, let's see. If I have this kind of square, or this kind of signal right here, right? If I added this whole signal together, what's the energy? Technically, it's going to be 0, but there is energy in this. Negative energy, positive, but there's some type of energy. What I'm trying to say is, this is T, this is amp, or something like that, is we add this whole energy, but you see how this is going to infinity, right? That means this is going to go to infinity. So let me just finish this problem. From minus infinity to positive infinity. Let me see. I know what's going on. E to the a of t. Does anyone bother if I do this? A squared? No? Good. At e to the j omega t. Oh God, this is going to haunt y'all. I hope you guys are happy. We could separate these two, right? Does that bother anybody? J omega t. All right. This is going to be an interview question. What's the absolute value of the imaginary term? It just disappears. It's just one. It's just a circle. It just spins around. Does that bother anybody? Because it just spins around. It's just a circle. That's the absolute value of this term. So it technically disappears. You guys following what I'm saying? So that means the term that truly matters, and I'll finish it right here. What page is this? 8, 9. Man, I'm running out of paper. So you have this. Let's see. Let me see. Energy is going to equal to a squared minus infinity plus infinity e to the alpha t, right? So if we know that this is going to be a positive term, right? But actually there's a u of t right here. If anyone understood what I was trying to do right there, right? That u of t, what does this u of t essentially do? Yeah, it just goes from 0 to infinity, right? Well, then when alpha or time goes to infinity, right? What happens to this term? Is it bounded? No. It's going to go to infinity. This term goes to infinity. Does that make sense? What I'm trying to show you? So this is how you would prove it. But I think there's a proof you have to say by, what is it? The Schwarz inequality. I think that's what he calls it. Schwarz. Or Schwarz equality, inequality. I think that's what it's called. Schwarz equation, where you're trying to prove this. This. I think that's what he was trying to show you. Well, actually, it's not this. It's actually this part right here. You're trying to prove that this is bounded. Is that correct? Any questions about that? Yes, yes?
So why don't you square the A?
Huh?
Why don't you square the A?
Why did I square the A? Well, because that's our original definition. Apparently there was a square term. I thought it was just absolute. Is that right? I read that right. There's a square. Which, I don't know why. Well, if you think about the capacitor, there is a square term, 1/2 CV squared, right, for energy of a capacitor. Right? Remember that? You guys want me to haunt you guys? Capacitor. Energy is equal to 1/2 CV squared. I think that's where this squared part comes from. There's a, what do you call it? A derivation somewhere, or someone proved it. I think that's what happens. Does that make sense? That's probably where the term is. Energy is squared. That good? So let's go over this other thing, because I think you guys understood what the power signal was, right? Let me just go over to you again. This is page 10, page 11. Sorry. Oh, where's my thingy? There it is. Let's just say, let me see. How do I want to do this? A e to the alpha t e to the j omega t, right? So in this equation, sorry, let me go over something I was trying to show you guys. Let's see. Yeah, this is I think this is correct, because let me see, page 6, page 10, page 9. This is actually kind of wrong. This is if I assumed omega is equal to 0. You guys want to see what it truly would kind of look like? This signal itself, it's actually going to look like this. Let me see. If alpha was positive, right? It's actually going to look like this. It's just a sine wave that goes up. It just spins around. But let's just say alpha is equal to 0, right? And A is equal to, 1 or something like that. It's just going to be this. There's no attenuation. Is that correct? If if this was just equal to 0, actually DC, but this just spins around, it's just a sinusoid. Is that correct? There is energy in this wiggly form, this wiggly wave. So if you wanted to, it goes to infinity, right? Based on this, AE to the AT, EJ omega T, he squares this term, right? And then what was the other thing he did for power? He goes from 0 to T. I'm going to just call it 0 to T. Does that bother anybody if I do that? No? And all we're doing is we're just measuring the power that's in from this period to this period, because we assume that this is bothering me because this is technically 0. So this is my dilemma. If you include this, there's technically no power, because it's just an energy signal that just goes to infinity. Does that make sense? Yes, no, maybe? So I'm trying to figure out what he was talking about in this picture. Define the value, because this is what's bothering me right here.
When I answered that, it was just, okay, we can assume we don't need to deal with negative numbers because of the UT function. You don't have to, it doesn't change, I guess, T squared, it's still that.
Yeah, because all it is we're just assuming just a time, just a blip in time. That's because, so basically what I'm trying to say is this unit step doesn't really matter.
It pretty much cuts it in half. Right?
It just cuts it in half, and we're really focusing on just this. And we're just squaring this, magnituding it, and that's all. We're just analyzing this and assuming it's a power signal, right? However, if we tried doing the energy signal for this, and I think that's where, let me show you this. I'm gonna do this. Is anyone bothered if I do this? E is equal to 0 to infinity time, right? Of AE to the alpha T, EJ omega T, right? And then if I were to do the following dt, A squared 0 to infinity of e to the alpha t. If A is equal to 0, what happens to this whole term? Right? So in reality, all you're doing is just worrying about this term. Is that good?
But because it's squared, it goes to 1, right? So do we even worry about that?
Squared?
And the whole,
This right here?
the absolute, but everything's squared.
Oh yeah, everything is squared. Because, well, 1 squared is just 1.
But
This right here, well, is just squared too. But what's the magnitude of an imaginary number? Or this phasor? 1. So it's just 1 squared again. So this is just technically 1 squared. And this is just 1 squared. So here's the other thing. Let me see if I can try to show you this. It's classical, I think. I think it's classical from what I think. This is 11. This is 12. You guys are getting your money's worth, huh? So we're trying to solve for the energy of this periodic signal, right? 0 to infinity of a squared, right? But we just have dt. What's that? A squared t, right? From 0 to infinity, right? What happens when t goes to infinity? A squared times infinity minus, well, 0. This just goes all the way to infinity. Does that make sense? That means this is not an energy signal. But if we do the power signal, from what I remembered, is if you do the energy signal, let me see, energy signal divided by, so we have this pesky time, right? We got to get rid of this time. So the only way to get rid of this time is to put another time there. Is that good? And I think there was a 2 right there, right? Because it's in half, I think, right? Is that correct? So what I'm trying to say is A, 2, T, but then there's another T term here to cancel this guy out. Is that what the book's saying, the proof?
Yeah, you kind of. That's pretty good.
Yeah.
He should really give me a book. Man, that's why I'm going to be his PhD so I can finish his book.
Above the very top.
T goes to infinity, yeah. That's truly what it is. So let me show you what I'm trying to say.
So this right here is the time that we're trying to take. So limit as t goes to infinity, right? This I've just made that a funny t, right? I'm taking these two to infinity. They're going to infinity, right? Infinity divided by infinity, right? Is just going to give you that a squared. So that means this is a power signal, but it's not an energy. It's power, not energy. Is that clear with everyone what I try to do? I have this pesky t term, even though I have this weird sinusoid. Now it makes sense when the unit step. Even our t is going to infinity. And the only way to get rid of that pesky t is with another t, so we can try to like average out that power. Is that good? Now let me see the other one.
That was evaluated at 0, right?
Yeah, that's it. That makes sense? Is there any questions about this problem? Any other problems? So I think what I was trying to, I think funny enough, I went over this first, then I went over this, because basically it leads, if you have an energy signal, you don't have a power signal. If you have a power signal, you don't have an energy signal. But if it blows up, like let me show you the paper that I had over here. If it blows up, like it goes to infinity, like an absolute value, or like, you know, what's a good equation? This is page 12. Are you guys familiar with this signal? Y of t is equal to t, u of t. Tell me, is this an energy signal or a power signal? Or neither? Draw this. It's going to infinity, right? And it's going to look like this, right? So if I add this whole thing, or absolute value it, square it, it's going to go to infinity. Now let's divide it by t. It's still going to go infinity because you have t squared over t. You see what I'm talking about? This right here is t. But if I square it and divide it by another t, it's still going to go to infinity. So it's neither. You like that demonstration? You wish he did this kind of lectures in class? You wish I was teaching that class for realsies? Yeah, because I give you guys quizzes every day. And then here's the other question, because someone was saying this. You guys wanted quizzes? Is that what you guys wanted? Yes, no, maybe? Yeah.
Or like reinforcing the topic.
Yeah, because...
We go over them very, very briefly.
Yeah, because...
I think it's more like we want examples of the work, because Dr. Schubert does not show off like what he expects on his tests and lectures.
Yeah, mostly proofs.
And it's like, yeah, it's hard. His homework is only worth 2%.
Yeah, and you're not wrong there. Funny enough, all the book examples, and I'll tell you this, the Schwam's outline stuff is basically an exam. If you look at the most of the problem sets, they're actually picked out. The definition ones are the ones he picks out personally. But most of those questions come from the Schwam's outline. So that's why he says, I don't know, are they doing it? So I can't really say anything about that, but I can try to show you practically what he's talking about. So I want to get a book so I can go over this more often. But is there any questions about this, about the quiz, about the exams or whatever? I don't think I'm going to have quizzes at all because that's going to be a burden on our grader, who, by the way, you're going over to grading, right? Has everyone turned in a code?
No, so I can just for this time, I just copy their code from the BMI
All right, so the grader is doing a good job at grading all your papers, but she is also running your code so that it's easier for her to grade. Try to have your submission, your MATLAB. Should we just still do the PDFs, or should we do something different and make them turn into code?
You said I submitted both for code and the PDF.
Yeah, ideally, because the PDF is easy to grade, but the code is so that we make sure it works. That's all.
I did the PDF and then the .info.
Okay. So I think there's a way to force it so that you have to submit two things, or because it runs on our thing. That's what I'm saying. So computer assignment 2, turn in your code so that we can run it on. Is that good?
Code and PDF?
Yeah, the code and the PDF so that she can run it on her end. Is that good? All right. How's the assignment? Do you guys like what's there? Have you guys talked about linear time invariant systems? What does that mean?
That's what we're getting into, right? Amplitude and amplitude and addition, is it?
Yep.
But we haven't gone over the block
Diagrams?
Yeah, we haven't done that yet.
Yeah, because I don't want to go straight into it. I think it's going to be a Monday problem. That's probably when he's going to start introducing these equations. Then what else is there? Do we have any other problems? What's going on? Let me see. What is this? Let's look at this picture. No, that's the other one. Hello. Rotate. Evaluate. Is this one of your exam problems?
Yeah.
Let's see. Was that page 13? Page 14. So let me just copy this. Evaluate. This was on the exam. Nice. He's really going vicious with this. Let's just go over this first one. You guys remember that one property? It's a derivative, or what do you call it? The integration Dirac delta type of definition. I think from what I remember, it's because you have a Dirac delta in here, right? So when does that equal 0 or 1? It's going to equal when time is equal to 0, right? So if we were to look at this just for time is equal to 0, okay, here's a better question. Let's just say it's at some random number, right? This is just going to be 0, right? And then, well, this right here, well, change of this times that. What is it called? I don't remember that property. It's not the sifting property. It's like a derivative sifting property. Because what I'm trying to say is if you have minus infinity to infinity of, let's say, some a of t, d of t, right? All you're going to get is just a of t is equal to 0. That's all you're going to get with this type of equation. But no, we're not doing this. We're doing this. A of t, where you're taking a derivative of, well, d, whatever, d of whatever this thing is, t, and then, dt. Does that make sense? And then I think there is a delta t. Yeah, there's so many t's in this, dt. So it's different. It's not going to be this. This is just sifting, but this is like a derivative sifting property. I don't have the textbook. This is annoying. Derivative sifting property. Do I have an image of that? T. No, that's not right. Where's the equation where you start doing that? Because there is a proof on how to do it. That's why his book is really nice. You can go over this. Eh. Even I don't remember this one. But there's a property with this where you have to take a derivative of this. There's a change. I'm not remembering it. Does anyone know what I'm talking about? It's like the last chapter of his, like the last page of his chapter 1. Does anyone have that book on hand? Yes, no, maybe.
The unit step.
Let me see. Derivative, delta. Derivative property of Dirac delta. Ah! Is this it? Let me check. Let's go to the AI generator.
Looks like it.
That doesn't. Oh, yeah. The nth derivative. Wait, what? This ain't right. Property of the derivative of the Dirac delta. There it is. So why is this important? So you have your signal, and then you have another signal. What? This don't make no sense. No, that's your play variable. Here's your play variable in there. You multiply your play variable by this, and then do that. What? That don't make no sense. Because this is all good fundamental stuff that I want to show you guys. Dirac delta function. First derivative of a Dirac delta function. Actually, better yet. Let me see if I can show you guys. Did he show you guys this? Page 15. Because I think it's going to have to do with this. Unit step. U of t, right? Remember the unit step? You guys like that little guy?
Here, I think the theorem that's at the bottom. I think that's what starts out.
Derivative shifting property when the Dirac delta is reversed. This is an exam problem. See, I think we should start focusing on the book. Oh, thank you for that, by the way. Here, take this. I want to try and go over what is going on because I want to look at this the next time we do this. What happens when you take a derivative of this? Right? When you have a derivative of a constant, what's that? It's just zero, right? Constant derivative, right? Zero, right? So in the end, at time is equal to 0, right? I'm just going to have this big funny spike. It's just going to go to infinity, right? Does that make sense? However, what happens when I try to go back and I try to do the integral of, actually, this right here is the Dirac delta t, right? Is that correct? What happens when I try to integrate this, the Dirac delta t dt, right? I add all this. When you add all this, it just turns to 1. Is that good? I think what he's trying to show you is there's something about that property that relates back to this, where when there is a change, you have something happening at that value. I wish I had a better answer for that, but is there any other questions before we close the day? I think the other question is, will I be posting these notes? Yes, no worries, so your comrades can know. Any other questions? No? If there's anything, email me. There's also Joanna, she's also grading all your computer assignments. Computer assignment 2.
I overheard the test got pushed back.
It got pushed back.
What is it?
Okay, so let me tell you this. If the exam does get pushed back, the assignment has to get pushed back. When you're praying, no. I'm talking to the guy. No, it's because the assignments and the exams are together. That's technically how it should be. So the assignment will be due the day before the exam, correct? Yeah. Was it midnight? I'll ask him, and then you guys start screaming at me, or actually, no, me or Joanna or both of us. All right, so
I'll talk to
Right
him.
now, we'll draw this plan, but then if any change, we'll know by Monday.
It has to be before the exam, but it's not going to be the original due date. So if it gets pushed, the assignment gets pushed. All right? Have a good day, y'all.
Thank you, sir.